Hi everyone, I'm Professor Sarah Rankin and I'd like to welcome you to Imperial's COVID-19 lockdown lessons. Today is lesson 10. Margarita is here as always and she will be looking out for your questions in the chat. So please post them about anything and we will be coming to them at the end of the session. So for these last 3 lessons, we're going to be focusing on the experience really of doctors working in hospitals that have had the first-hand experience of treating patients with COVID-19. We will hear about how the whole hospital system has had to rapidly adapt to treat patients and obviously to minimise transmission to staff and other uninfected patients. So in the first of these lectures, we're going to start with the story of Jakob Mathiszig-Lee. He's an anaesthetist and he's working in a West London hospital. He originally did his medical training at Imperial, and we're going to hear about his experience on the wards and how that led him to connect back with the bioengineering department here at Imperial to help him design and build a new low-cost ventilator that the team have called the JAMVENT. Now, there are over 40 members of this team who have been working on this project during lockdown, and these include research fellows and postdoctoral scientists, and also a lot of students have been involved in this project. So really exciting project for the students to be working on. Today we have 4 of the sort of key members of the leadership team that have really been involved in the project from the start and been really critical in driving it forward. And so first of all, I'd like to introduce you to them, and I thought we'd have a quick chat with them just to find out a little about their backstories. And I think we'll start with you, Jakob, because you're sort of the person that initiated this project, but maybe just tell us a little bit about yourself. So you did medicine at Imperial. How did that come about? Did you always want to be a doctor?
Yeah, so hi, my name's Jakob. So I am currently an anaesthetist, but yes, did my undergraduate at Imperial. I'd generally been pretty committed to medicine for a long time. I had a bit of a wobble. I very nearly tried to get on the computer science with AI course at Imperial. Yeah. But other than that, have generally been kind of very, was sort of very keen on medicine. So I did my undergraduate at Imperial, so that was 6 years, because that also includes a degree in neurosciences and mental health that I did as an integrated course. Mm-hmm. And then since then I've been working sort of around the country as an anaesthetist. And I came back to the college about 2 years ago now as an honorary clinical research fellow. So what that means is effectively in some of my spare time, I do some research on, again, going back to the kind of what I maybe nearly did. So I'm doing some data science research, so using AI to try and predict mortality in patients who are having kind of emergency bowel surgery.
Really interesting, really interesting. Yeah, there's a whole new field of medicine now that is really rapidly growing, which is using all, the AI and big data. They're sort of 2 big sort of in terms of computing and everything, but they're really sort of making big changes in medicine, how we treat people and thinking about, going forward. So now we've also got Dr Joseph Sherwood here. Joseph, tell us about yourself and your guitars.
Yeah, well, actually, after leaving school, I was a musician for a few years. And it was doing that and riding around a motorcycle to teach guitar at schools, and the motorcycle kept breaking down. And after a while, I figured I should probably learn how to fix it. And that led me towards mechanical engineering, which was what I did my original degree in at King's College. Yeah. And then when it got to the summer of my 3rd year, I was offered a research project looking at how fluids passing buildings might make them vibrate. And that kind of got me into studying flow. And then at the end of my 4th year, I had the option to keep studying that, or it was suggested to me I could study how blood flows, and that sounded a lot more interesting, and I haven't really turned back since. So I've been doing study of blood flow, study of the flow in the front part of the eye called the aqueous humor, and now working on breathing and the flow of air in the lungs as of March.
And just to put that into some context, because I know about this, a little bit about this from a patient perspective. So that study of the flow of the aqueous humor through the eye is really important, because if it goes wrong, so you have liquid coming in essentially to your eye and then going out, and if it goes wrong, then you could have a buildup of that liquid, and your eye will then sort of change, the sort of shape will go a bit more bulbous, and that's going to affect your seeing ability, your ability to see, and that is one form or one cause of glaucoma. Is that correct?
Yes, exactly. Yeah, so I build technology to help glaucoma researchers test hypotheses, ask questions about whether this protein or this drug might help to lower that pressure, and I build the technology to allow them to do those tests.
Yeah, so this is, and that, I think that's really a key thing. So I'm a pharmacologist, so I'm the person that would be developing the drugs, and we're always looking for ways of testing, and glaucoma is a classic example of something. It's very difficult to have a sort of a good model of it. So yeah, the fact that we're doing, I mean, lots of people working with the bioengineers, because they can use their sort of engineering tools and know-how to develop these models. But it's also interesting that you're talking about blood flow, because earlier on, right at the beginning of these lockdown lessons, when we were talking to the chemical engineers, they were talking a lot about, in terms of chemical engineering, a lot of that is about pumps and blood and things flowing from one place to another. And they also do a lot on blood flow, which I wasn't aware of. And obviously, you know, for us in the National Heart and Lung Institute, we do a lot on blood flow and blood vessels as well. So it is interesting how you have people across college that all have similar interests, but we're coming at it from very different ways. And that's why at Imperial we have something called the Networks of Excellence, and we all get together. So if we, you know, people that are studying blood flow, for example, would all get together, whether they're engineers, chemical engineers, bioengineers, or biologists. So yeah, and those things are fun again, because they can lead to other sort of more interesting projects. Anyway, so moving on, who should we go to now? Maybe Jennifer Frattolin. So Jennifer, tell us about you. You're Canadian, yes?
I am Canadian, yes. And I'm actually here in Canada at the moment. So
are you? I didn't realise that. Whereabouts?
In Toronto.
Yeah. Okay, nice.
Yeah, it's nice. Weather's beautiful. So I born and raised in Canada, and I pursued a degree in mechanical engineering. So my background is mechanical engineering, both from my undergraduate all the way up to my PhD, which I completed at McGill University in 2018. So my desire, I guess, to go into bioengineering was really rooted in the fact that I loved medicine, but I did not want to become a doctor.
Yeah. And
so I thought that doing engineering was a fantastic way of being able to mix the two. So even though I did mechanical engineering in my undergraduate, my doctorate degree was completely focused on medical devices and bioengineering. So it was great. And then I moved here to London to do my postdoc.
And what brought you to London? What was the, why did you decide to move? Just to live in a different place, or?
I mean, one of the reasons was, I'll be completely honest, it was for Imperial College. I mean, the name of Imperial College is world renowned, and it's a fantastic institution. And I knew that coming to Imperial College for my postdoc experience would be such an incredible asset. And that was part of the reason. The second part was, my current PI that I'm working with, Professor James Moore, is really a wonderful PI. He does really exciting research, and really kind of at the avant-garde research in lymphatics. And so that was one of the other reasons, obviously, that I came here.
Right. Okay. That's interesting. So has it lived up to your expectations?
Yeah, absolutely. I think it's been a really wonderful experience. And what I really would say is that I've had a lot of freedom to explore a lot of interesting research facets that I didn't think that I would be able to. It's been a lot of learning as well. Mm-hmm. I've done my PhD more in cardiovascular side, and now I've switched into lymphatics and immune research. And as a result of that, I've had a lot of learning experience. I've learned a lot of new research techniques, and that's been really great.
Right. Yeah. So I work in a department that's full of immunologists, so we know about lymphatics. I think lymphatics is something that hasn't come up in these talks yet, but they're very important in terms of the immune system, because they're sort of I don't know if you cover lymphatics actually in your sort of GCSE A levels, but they're like another. So if you think about all your blood vessels, they are sort of like the A roads, then the lymphatics could be like the B roads. They're a sort of another way of cells getting and trafficking around your body. And actually, if you look in the lymphatics, they're very white, because it's all the leukocytes that tend to be in there. So the T cells and B cells and things like that go via the lymphatics. So we won't go into that in detail now, but just to show, when you're doing your GCSEs, A levels, there's still like masses to learn once you get to university. Yeah, so I love engineers getting into medicine. I wonder, so I was going to ask you why you didn't want to do medicine. I just wondered if it was similar to me. I've got a complete phobia about blood, so that's why I didn't want to do it.
No, actually, that was not my issue at all. I don't mind doing all of that kind of thing. It was just more, I like also like building things as well.
Yeah.
And I think that's one of the highlights of being an engineer is being able to design things and actually build things. And there's something so satisfying, I think, about that, while still being able to have a really strong impact on society and people's health by doing bioengineering.
Yeah, because certainly, definitely, if we look at this project, you're developing a ventilator which, could go around the world and have a lot of impact on people's lives around the world. So yes, right. So finally, we're on to Michael. So Michael Madekurozwa. I'm useless at that pronunciation. Sorry, Michael. Yes, tell us about yourself and pronounce your name correctly for me.
Michael Madekurozwa. So I'm Zambian born. I spent the first 8 years of my life in Zambia, the next 8 in Zimbabwe, and then I moved over to the UK for my A levels, and I've stayed here ever since. So during my A levels, the plan was to actually study medicine, but then I found out about the graduate entry route into medicine. So I thought if I go into bioengineering and I enter medicine in the 4th year, I could get 2 degrees for the price of 1. But I enjoyed bioengineering so much, I just stayed in the field ever since. So I did my undergrad and PhD at Imperial. My undergrad, Joseph Sherwood and Dr. Darrell Overby were both my supervisors for it. So in my final year, and then I also moved to my PhD because they were such good supervisors. I stayed on with them, did my PhD with them, and yeah, here we are.
Great. Cool. Okay, so let's get on to the science then. Thank you guys for giving us a little bit about yourselves. And I think that Joseph, you're going to kick off telling us something about a little bit more about what bioengineering actually is, I think, to start us off.
Yes, I will. We've got the slides up.
Great.
Okay, And okay, so I'm going to start by talking a little bit about what bioengineering is. So bioengineering is a lot of different things, to give you an overview here. The first one we've got a picture of here is biomechanics and mechanobiology, so studying how joints work and how we can actually lift and move things around. It's biomedical sensing and diagnostics in imaging, MRI scanners, and how we analyze that data. It's computational modeling, so we can take medical data and predict what that might tell us about diseases. It's medical devices, designing technology to actually test for indications of disease or for ways of treating it. It's molecular and cellular bioengineering, understanding how mechanical forces interact with cells. It's neurotechnology and robotics. How can we actually use engineering techniques to interface between the human world and the robotic world? And also regenerative medicine and biomaterials. So can we build bits of new tissue that we can put back into patients and things like that. So bioengineering is a very, very broad world, but there's one kind of underlying theme that holds the whole thing together, and that is the application of engineering principles to biological and medical problem solving. So as it's such a broad subject, and because of the project we're talking about today, a lot of the context of what bioengineering actually is, we'll show you as we actually work our way through these slides today. And we're going to talk about one specific problem, which you may have guessed what it is, and our solution to it. So the problem came with COVID-19. As Sarah mentioned earlier, Jakob was working on the wards with patients who needed ventilation. So we can see with this patient here, there's a tube in his throat, and he's connected up to this machine here, which is a ventilator. And that's basically doing the job of breathing. So on the beginning of this whole project, on March 15th, Jakob came to talk to us in the Department of Bioengineering because of all the things we're able to do, as pointed out in the previous slide. So the first thing to do is to identify what the problem is. This is a fundamental part of the engineering process. So we'd start by looking at what exists already. So there are many ventilators available from different manufacturers. This is a picture of a Draeger ventilator, which are one of the world leading products. And they have very complicated designs, lots of different functionality, specialist components. And under normal circumstances, that complexity is not a problem because there's plenty of time to build the systems as they're required. But with COVID-19, the need increased, and there was an estimate of about 1 million worldwide requirement. And that's obviously a huge number, and there's just not the capacity to produce this kind of machine on that timescale. And so we needed a low-cost, easy-to-manufacture ventilator to cope with COVID-19 patients. So we've established what the problem is now. So we set about working out the solution. So this was day 5 of the project. This is a very basic setup. You can see all the mess in the lab, and we're just throwing things together with what we've got. We're a little bit of software to kind of control it, but it's showing a basic proof of principle. It's kind of working. Then we go through refining the design and improving it. So this is showing we're starting to get waveforms there that look like a real ventilator. We've tidied up the design. This blue thing here is actually a kid's party balloon, which while it had some benefits in terms of making the device more compact, probably wasn't a good long-term solution for a medical device. So in the next version of the prototype, we got away from that. You can just see a slightly larger bottle here. This is a system that Jakob came in after working on nights and helped me build. And this is the basic layout that we're still working with now. So we've got to there within 13 days. This was our first full portable prototype. You can see it runs off a laptop computer. It's a tight little box with all the electronics and pneumatics inside it. We added a couple of extra modes. I won't go into these too much detail, but patients with COVID-19 have a lot of secretions in the lung you have to suction out, but we need to maintain the pressure in the lung while we do that. And also, when you come off ventilation, you need to help the patients recover their ability to breathe because the muscles of the lungs will actually have weakened over time. So we added that all by day 35. So that was 5 weeks to get to basically the solution we're at now. And this is a little video of Jakob demonstrating it. We won't kind of talk through it in detail, but we've got a head here that actually features in the new Batman film. We can't tell you what role it is. And a mock lung that Jen's going to talk to you about. We've got the ventilator here. and the software being run on the code there. So, as an overview of our talk today, we're going to first hear from Jakob about the clinical consequences of COVID-19, why you might need a ventilator in the first place. Then I'm going to talk to you a little bit about some of the physics of the airflow in a very easy to understand way, hopefully, and tell you how a machine can actually do the job of breathing when the patient can no longer do it. Then we'll move on with Michael, who's going to teach you how we actually built JAMVENT and what that involves. And then Jen finally will teach you about the mimicking the human lung and how we do that so we can actually test the system we've built. So over to you, Jakob.
Okay, hi. So as I said, my name's Jakob. I'm an anaesthetist and been working on the kind of front lines at the Royal Brompton Hospital with COVID-19 patients. So I'm just very quickly going to go through the kind of clinical reasons that we need ventilators in COVID-19. So what do lungs do? Well, they're basically a huge area. It's about half a tennis court of kind of area for diffusion of gas. So you breathe in, the oxygen from the atmosphere comes out of the air into your bloodstream. And really importantly as well is that oxygen gets metabolized to carbon dioxide. And so the lungs excrete the carbon dioxide as well. They don't just do that. Lungs are pretty cool because they've got such a massive surface area. They have a really important role in drug metabolism, which I think is really interesting. So actually, one of the big pathways of how you manage your blood pressure is actually regulated in the lungs. That receptor that I'll talk about on the next slide is actually involved in the kind of pathology of COVID-19. And just fair warning, just have a quick look away now if you're feeling a bit squeamish. So this is what lungs look like. So these are actually pig lungs, so slightly larger than a human, but kind of pretty much the same. And you can see there that they're kind of inflating and deflating, and actually that they're just really, really soft. You can tell they're kind of very jelly-like consistency, and actually they're very fragile tissue that's very easily damaged for any reason. And so what does COVID-19 do to those lungs? Well, effectively what you have here is you have a round virus, a coronavirus, which is SARS-CoV-2, which is actually what the virus is called. And what this is covered in is all these spiky proteins, which are imaginatively called spike proteins. And these act as effectively like little keys in locks, and the lock in this case is a receptor called ACE2. And now that's one of those receptors I was talking to you about that's involved in blood pressure regulation. And interestingly, it's potentially one of the reasons that we've seen different patterns in disease in different ethnic groups, as different groups in the kind of around the world have different expressions of that. And so what does that actually involve? Well, effectively, you'll have nice healthy lungs up here. You've got a kind of tree and bud. So actually those lungs are made of tiny, tiny little balloons called alveoli, which is where the gas exchange takes place. And as soon as you get infection, you get inflammation. So you get kind of the body's own immune system releasing these chemicals to try and fight the virus. But this causes inflammation, so kind of raised temperatures and fluid buildup. And you get pus from all the immune cells kind of rushing towards the area of infection. And what that does is that clogs up the lungs with kind of pus and things, and kind of means that massive area of lung for gas exchange becomes less and less able to do so. And actually, what does that look like? So I'm going to turn you into radiologists in about 60 seconds here. So this is a CT scan. So this is an axial view, so a slice through, not the stomach here, but the chest about here. And actually what this shows is, this shows normal lung in this case. So this is one of those donuts that you'll see people go through on medical TV shows. And just very quickly, what I want you to see is that in the middle of it, you've got a heart, you've got a lung either side of it. You've got white bits at the back, so you've got the spine at the back, which is bone. And so anything that's air-filled is dark. Anything that's very dense is white. And so when you go from this normal lung to this, you can see why people have problems with their breathing and COVID-19. So you can see that there's much less dark stuff. It's all become kind of white, inflamed, what we call consolidated. So it becomes, very wet and spongy. And actually, there's bands of sort of dense white matter, which is fibrosis. So where actually the lung starts to become almost like wooden because of all the inflammation. Now, what do we do about it? We put people on a ventilator. And so what that involves is, as an anaesthetist, I would give a person an anaesthetic to put them to sleep and to paralyze them. And then I use this thing called a laryngoscope, which lifts up the patient's jaw and allows me to see down into their trachea, so their windpipe. And then we put what's called an endotracheal tube down. So this is a tube with a cuff on the end that allows me to go directly from outside the mouth into the windpipe and seals it off and allows me to connect a ventilator. And so this is just a diagram of doing it in a person, but actually people do it in lions and gorillas. It's the same process, although with a lion you don't, and cats actually, you don't need to use a laryngoscope. You can just go straight down. Okay, so that's my little bit. I'm going to hand you back to Joseph.
Sorry, I'm muted, Joseph.
Thank you very much, Michael. So I'm going to talk to you a little bit about the physics of how a ventilator can breathe for us. And it's very simple, really. We're dealing with the thing called pressure. So what is pressure? This is a container here, and inside it we're going to put some gas particles. So these gas particles are all kind of bouncing around, and every now and then one of them will bounce off the walls of the vessel. And when it bounces off the wall, it applies a force to that vessel. And if you take all of the particles bouncing off the walls and divide that by the area against which they're hitting, that is the pressure. So that's what pressure is. Now, if we add more particles into that same container, they're going to bounce off the walls more often. So we're going to have an increase in the pressure. At the same time, if we make a larger version of the vessel but have the same number of particles in it, they're going to collide with those walls less often, and hence the pressure is going to be lower. And this latter relationship is known as Boyle's law. So it says the pressure times the volume remains constant. So if we've got the same volume and more particles, then the pressure goes up. But if we have the same number of particles and the volume increases, the pressure is going to go down. That's going to be quite important as we go through understanding how we can drive a ventilator. So flow is driven by a difference in pressure. If you have a region of high pressure over here on the left and a region of low pressure on the right, and you connect them together, particles will flow from the side with the high pressure to the side with the low pressure. And they will flow with what we call a flow rate. And the flow rate is the amount of volume you can move from one place to another in a given amount of time. So maybe a liter unit. Increase the pressure up here, there's going to be more particles moving quickly, and we're going to have a high flow rate from the high pressure to the low pressure region. So we can say that the flow rate is actually proportional to the pressure difference. And you can see here the different pressure differences between the downstream and the upstream pressure. So how does this actually play a role in how we breathe? As a bioengineer, you should start by saying, how does a human breathe? And then you can think about how a machine can breathe instead for you. So this thing here, which looks a little bit like a sad frog, is actually a diagram of our lungs, and this green thing here is a diaphragm. So when you want to breathe, your diaphragm contracts, and what that's done there is that's increased the volume of the lung. So we know from Boyle's law that if we increase the volume of the lung, we're going to decrease the pressure in the lung. So the pressure outside is 0. It's actually the pressure of all of the air molecules on top of us. It's called 1 atmosphere of pressure, but we treat that as 0 pressure. And the pressure inside the lungs is now lower. So now we have a pressure gradient, and we know what happens when you have a pressure difference. Flow moves from the high pressure to the lower pressure region. So that fills up the lungs until the pressures are the same. Now, what happens next? The diaphragm relaxes, and in these alveoli that Jakob told us about before, there's actually a rubber-like material called elastin. And so when we release the pressure, they get smaller. That rubber band basically contracts, it's back to its normal size. That decreases the volume in the lung and hence increases the pressure in the lung. When the pressure in the lung increases, that generates a pressure gradient out of the lung, and so flow goes back out and we have exhalation. And so if we look at that at a full cycle, that is how a human breathes. What does a ventilator need to do? So we need to start by applying, during inhalation, a pressure that's higher than the lungs, so air will flow in. So if we connect our lungs up to a high pressure source and let it flow, the lungs will expand. And here we've sort of seen the pressure inside the lungs increase and the volume inside the lungs increase. Now that's because there's more particles being added. So Boyle's law doesn't actually hold here, but it was a useful way of understanding the normal breathing process. Okay, and then to exhale, we've already got the large lungs. What we have to do is connect to a low pressure area, and so that we can set up a pressure gradient in the opposite direction, and then the volume comes back down to the baseline, and you see the pressure here actually doesn't go to zero. We need to keep it slightly above zero at a level called the positive expiratory end pressure, or PEEP, in order to make sure that the alveoli stay open and do the best that we can do for that large half tennis court surface area. So my last slide is about how you choose the best design. Part of engineering is understanding the physics, and then part of it is how that interacts with the real world. And there are lots of different ways that we could build a system that could control pressure. But what we have to do is do a trade-off between all of those different methods that we could use and some real world factors. These include cost, quality, so the performance, the modes of operation, the different things it can do, and time, so how easy is it to manufacture. We know that was a really critical part of this design. So we can imagine a little triangle here: cost, quality, and time. Normally you choose two of these, but actually it's a little bit more complicated than that. So existing ventilators are very high quality. They're slow to build and expensive, but they perform an awful lot of modes and they do it very accurately. And in addition to our team, there were lots of teams around the world building very, very quick and easy to build designs, which were also very cheap, but they often didn't have the performance that was necessary. So with the JAMVENT design, we went somewhere in the middle. We didn't quite have the quality for the all of the modes that are offered in ICU ventilators, but they're not necessary for COVID-19 patients. And it might take a little bit longer to manufacture than the simple designs, but we decided this was the best approach. And now Michael is going to tell you about how that actually works.
Hello, so I'm going to tell you how you actually build a JAMVENT system. So first of all, how does a JAMVENT system actually ventilate a patient? Well, we start off with the preparation of a breath at the end, at the desired air to oxygen ratio and volume. We then deliver the breath to the patient, and lastly, we allow the patient to exhale. The repetition of this cycle is what we term as ventilation. So what are the components inside the JAMVENT system? I'll take you through the components inside the system, and then we'll go through how the system actually operates. So here's the system over here. We have oxygen and air supplies, which provide the oxygen and air that the system requires for the patient. We have a reservoir in which a single breath is stored for the patient prior to delivery. We have open or closed valves here, 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 and here. Now with these valves, we have small little circles in the valves which denote the valve being closed. And if there's no circle in the valve, that denotes the valve being open. So in this case, the valve is open, so oxygen will move through the system and to the reservoir, but it won't go down because this valve is closed. Note that these valves are not proportional solenoids. So typically in high-end systems that perform similar to the JAMVENT system, proportional solenoids are used. But the problem with proportional solenoids is they are specialist components, which makes them difficult to source. So we went with on-off valves instead, and these on-off valves are much, much easier to procure. The system has an oxygen sensor, which measures the oxygen of inhaled air. It also has a pressure transducer, which measures the pressure inside the reservoir. And this is important because when we're delivering a breath, we want to deliver a set tidal volume. And the way that we measure volume is by measuring changes in pressure through Boyle's law, as was discussed earlier by Dr. Joseph Sherwood. So we have a pressure transducer here as well, which measures the pressure in the lung of the patient. This is important for two reasons. Firstly, as a clinical output, so the clinician can see what's going on in the lung in terms of pressures. And secondly, as a safety mechanism. So if the pressure in the lung goes too high, the system will detect it and act accordingly to decrease it. Lastly, the system has pressure release valves here and here, which limit the pressure that the system can actually get up to. These type of safety mechanisms are typical of ventilators because, as was mentioned by Dr. Mathiszig-Lee, ventilators ventilate lungs, and lungs are very, very delicate organs. So they have to have, ventilators have to have several safety features to prevent them from damaging the lungs. So let's go through the first step. In the first step, we need to load oxygen for a breath. We need to load oxygen and air for a breath. So we start off by loading oxygen by opening this valve. So the first valve opens and oxygen moves into the reservoir in preparation for a breath. Next, air moves into the reservoir in preparation for the breath. Once the volume is loaded for a breath at the correct at the correct ratio of oxygen and air and at the correct volume, the breath is now delivered to the patient by the opening of valve C, which is this valve over here. And we'll visualize that now. And there we go. And the final step of ventilation is exhalation. So exhalation requires the opening of valve D. So this valve over here, which will open the lungs to atmosphere. There we go. So we'll go through this visualization one more time. So we have air and oxygen loaded into the reservoir. We have the reservoir air moving into the lungs, inhalation. And finally, we have exhalation. And the process repeats. So the pneumatics of the system are built up of push connectors and threaded connectors. And the reason why we built the entire pneumatics out of push connectors and threaded connectors is because these are easy to source, easy to connect, easy to disconnect, and so easy to clean. Typically, systems are built out of custom-built pneumatics. And the problem with custom-built pneumatics or custom-built manifolds is they're difficult to produce at scale, and they tend to be quite expensive. Let's actually look at what's inside the JAMVENT system. So if we take the JAMVENT system apart, we'll notice that we have the pneumatics at the top, which are the parts that we've been talking about all along. But beneath the system, we have the electronics. We built the system with this type of architecture to make it easy for engineers to work on the pneumatics without disturbing the electronics, or to work on the electronics without disturbing the pneumatics. I'll now hand you over to Dr. Jennifer Frattolin, who will talk about mimicking a human lung.
Okay, perfect. So first of all, why do we want to test ventilators? Why do we want to test JAMVENT? Well, it's really important within the design process to be able to evaluate the performance of our actual ventilator. And so how do we actually do that? Well, obviously, particularly during the design process, we want to avoid using human testing. Obviously, there's also a lot of ethical concerns regarding human testing. So it's necessary for us to develop a lab-benched system that will allow us to test our ventilator, combining our knowledge both of lung physiology as well as the principles of engineering in order to simulate the behavior of a lung. So what exactly do we need to mimic? So when we talk about the lungs themselves, there's two principal components. So first, we need to replicate lung compliance. And second, we need to replicate the airway resistance. So with respect to the lung compliance, that is defined as a measure of the lung's ability to stretch and expand in order to be able to hold air. And mathematically, we can express this as the change in volume over the change in pressure. So let's look at this in a little bit more detail. So what exactly is compliance? So let's imagine that we have a thin wall balloon. So at a lower pressure, the balloon will inflate as shown. And that balloon will continue to inflate as we increase the pressure that's being applied. But what happens if we have a thick-walled balloon? So at that same low pressure, the balloon will expand to that same volume. However, as we start to increase that pressure, you'll notice that because the thick-walled balloon has a higher stiffness, the actual amount that the balloon inflates for a similar pressure is actually less than that thin-walled balloon. And that's because of its lower compliance in comparison to that thin-walled balloon. And so we would actually need to have a higher pressure in order for it to inflate to that same size as the thinner balloon. So talking about lung compliance, so lung compliance can vary during respiratory distress, such as in COVID-19. And this is obviously a dynamic change, and it can vary depending on the severity of the disease. So with respect to particularly COVID-19, typically we see an increase in lung fibrosis, which was kind of mentioned by Jakob. And as we have this increase in hardened tissue, this is going to obviously overall decrease the compliance of our lung. So now, how can we actually build a system that has that variable lung compliance in order to take into account disease severity? So we wanted to, when we were simulating lung compliance, we really wanted to use basic engineering principles. And so in order to do so, we utilized something called a leaf spring. And a leaf spring, if you can imagine, is if we have a plastic sheet that's fixed at two ends and we apply a pressure to the inside of the sheet, it will begin to bend. And the degree to which it bends, it depends on the overall stiffness of the material. And by changing the stiffness of the material, we can actually alter the overall compliance of our test lung. Now, the next thing that we wanted to do was use easily sourced materials. So for example, as you can see in the video, we used a hydration bag that you would use for hiking to replicate our lung. And we used Perspex sheets that could be layered in order to act as our compliance. And then we also used aluminum hinges on either side to complete our leaf spring design and to actually anchor our Perspex sheets. Now, overall, the design was very simple to construct and replicate. So utilizing that leaf spring made it easy to build, which required very minimal materials in order to build it. And then, as shown in this video, it was quite easy to assemble and disassemble. So that was the lung compliance, but what about airway resistance? So by definition, airway resistance is the resistance or the opposition to airflow in the respiratory tract due to friction. And mathematically, we can express this as a change in pressure over flow rate. So again, let's take a look at, well, what is resistance? So imagine that we have two containers of gas particles that are connected by a narrow constriction or a narrow corridor. And there's an imposed pressure gradient. So gas particles will flow from the container of a higher concentration on the left to the lower concentration on the right. So this constriction, however, will result in less particles actually being able to physically get through to that lower concentration container, simply because there's just not enough space for those particles to actually pass through. However, the constriction also increases that interaction between the gas particles and the wall, which results in higher frictional forces, which will also overall slow the flow rate. So therefore, that decrease in flow rate leads to an overall increase in our resistance. So now, similar to lung compliance, airway resistance will change depending on the severity of the disease. So when an airway becomes inflamed, this typically results in swelling as well as other inflammatory processes. This results in a narrowing of our airway. And like I just kind of demonstrated in the previous slide, this actually increases the overall resistance of our airway. So how do we actually replicate the airway? So obviously, when we want to replicate a diseased airway, we want to be able to increase our overall airway resistance. And so we, first of all, need to increase the friction that the air is actually exposed to. So what we did was we used a combination of wire and fabric gauze. And by placing this in the flow path, this changes our airway into a series of very tiny little airways, which increases our overall surface area that the air is actually exposed to, which increases our friction. And what we can do is we can layer these wire and fabric gauzes in order to increase or decrease our resistance. And then we can use a 3D printed holder to actually hold everything in place. And then we can place this into a series of threaded tubing connectors, which will allow us to connect it to our overall test system. So here is our actual complete system. So you can see here on the left, we have our JAMVENT, the ventilator. And then in the middle here, this is our resistance. And then on the far right, we have our test lung, which is our lung compliance. So now we are equipped to actually test our ventilator, but how? So we've developed a software interface that allows us to control and manipulate the various different ventilator modes and parameters. So on the left-hand side, you can see the user input panel. So this is where a clinician like Jakob can change the overall input parameters of the ventilator, such as our respiratory rate or our tidal volume. And then on the right-hand side here, you can see the actual patient outputs. So these are actually calculated and updated with every breathing cycle. And in the middle, you can see our pressure and flow rate waveforms with respect to time. Now, on the right-hand side of the screen, you can actually see one of our test lungs inflate and deflate. So this scenario depicted here is actually one of a severely diseased lung. So we have a very low compliance lung with a very high resistance in the airflow path. So this is really evident by kind of the high peak inspiratory pressures that you can see during inhalation. But actually, when you look at the lung itself, we have minimal inhalation of the actual test lung. So because of this, we've actually modified our ventilator settings accordingly so that we are actually delivering a smaller amount of volume of air, but at a faster rate.
Okay, so I'm just going to bring this back round to where we started. So what is bioengineering? And in this aspect, it was solving a given problem about ventilator shortage, and that used a range of skills. So that used, firstly, we needed to understand the physiology. Then we needed to do some mathematics to understand the physics of the airflow. We had to build things. We had to do some electronics. We had computer-aided design work. We had software and computer programming and data analysis. And all of these things are critical bioengineering skills, but one of the most critical of all was our ability to work together as a big team. So this is a good chance for me to thank the rest of the team. We've got Professor Moore, who teaches in the Department of Bioengineering. These other four guys, Daniel, Axel, and Willie, make up with the four of us the core team. And then we had a large group of students who helped us out with this project doing various different parts. So it's been a really great team working effort. We also had some help from Imperial College and the Royal Academy of Engineering, and lots of friends of ours and other people at college who just donated their time to the cause overall. So I want to thank everyone, and with that, we'll open the floor to questions. Thank you.
Great, thank you. That was really brilliant, and yeah. I've got lots of questions myself, but I'll go first, Margarita, to questions that you might have or from anybody that's watching.
Yeah, hi Sarah. I would like at first to thank all of you for the presentation. I have a lot of questions, and I think JAMVENT is really cool. So Max, one of our listeners, he's currently in year 12. And he wants to study mechanical engineering at Imperial, but he doesn't like bioengineering. So he's wondering what role did mechanical engineers can have in terms of dealing with COVID-19?
I mean, the interface between mechanical engineering and bioengineering is where you choose it to be. As I mentioned earlier, I trained as a mechanical engineer. So if the mechanical engineer had been on our team, they would have done much of the same job that I'd done in terms of the technical parts. So the software programming is actually mechanical engineering. The understanding of the gas flow, the pneumatics is also all mechanical engineering. I also have colleagues who've designed things like visors that can be 3D printed for PPE applications as well. The computer-aided design skills you use for that are also mechanical engineering. So there's lots of applications.
Yeah, we have a lot of 3D printing going on at Imperial, don't we? I know in bioengineering you use them. And also it's interesting how in the materials department they are making their own biomaterials, which I think Joseph mentioned at the beginning, making materials for regenerative medicine. So again, those can be 3D printed. And also we have ED. I think you think about 3D printing with plastic, but we also have 3D printers for metal structures as well, which, again, allows you to do lots of fun things. And that lots of those are available for students in our advanced hack space. So if you want to sort of design something and make a prototype of it, there's a facility for you to do that. So yeah, great. Margarita, sorry, any others?
Yeah, I have a question. I'm really curious to know why you chose to name JAMVENT instead of something else. What it stands for, JAMVENT?
Yeah, so it was a bit of a spur of the moment decision. We were focusing a bit more on the engineering than the naming, but we put down our names, and you may have noticed I'm Joseph. My middle name's actually Michael, so it's JM there. We've got Jakob Mathiszig-Lee, Michael Madekurozwa, Jennifer, and James Moore is the other one on the team. Oh. So, and as you may have noticed, me and also Professor Moore are musicians, and so improvising is also known as jamming. So JAMVENT kind of became the name, and we're stuck with it for better or for worse.
That's really nice.
So I'm just intrigued. So if you're
Sarah, we can hear you.
Sorry. Can you hear me now?
Yeah, you're back.
Yes.
Sorry, glitch. Yeah, I was just saying that if I was developing a drug, as we heard from one of the other lectures, to take that drug and be able to give it to patients, we would need to do lots of testing. First of all, in animals, sort of toxicity testing, and then testing to see if it had efficacy, so if it worked. And then we would have to go through lots of patient studies. So first of all, healthy volunteers, and then with sick patients. So this is obviously, it's not a drug, but it is something that you're going to use to treat patients. So what are the what's the regulatory processes you would have to go through with your JAMVENT to actually be able to use it on a patient in this setting? So
yeah, so there's basically I suppose there's two strands to this. There is the normal process, and there is the COVID process. And so there's the medical device world, understandably, particularly for something as important as a ventilator, has a lot of regulation about it. So I guess one of the less appealing sides of doing this kind of rapid kind of medical device development is the absolute gargantuan amount of paperwork you have to do. But alongside that, there's a lot of testing that goes with it. So actually, as part of ISO standards, these international standards that govern how a ventilator should perform, they have lots of scenarios just to try and kind of really stress out so you have to prove that you're precise and that you're able to deal with kind of complicated patient conditions before you even get to sort of testing. At the moment, we've applied for what's called emergency use authorization. So because of the nature of COVID, there just isn't the time to do the formal tests that you would normally do. And so if there was a scenario in which a country is overwhelmed, if we get approval for this EUA, then countries would be able to use it kind of as an emergency use. But depending on funding or not, then we can move on and do kind of all the kind of similar sorts of steps. So initially some clinical trials. With a device like this, though, we slightly have an advantage in that you can kind of skip the phase 1 studies, which are the kind of studies in well patients, because you're not allowed to anesthetize people and ventilate them for weeks on end just to prove a device works.
Okay, so yeah, that's interesting. And I mean, we're lucky in the UK. As of to date, we haven't had the situation where we've run out of ventilators for patients. But I saw on the news today a doctor from ICU in Texas saying that he had 5 young patients that needed ventilators, and he only had 3 ventilators left.
Yeah.
So there are clearly, potentially that situation will occur.
Yeah, and what actually, the reason I sort of sent the email to the Department of Bioengineering was, a lot of my colleagues at the moment where I work are Italian, and actually they had friends in Bergamo, which is one of the worst hit towns in Italy, and they were down to their last couple of ventilators at 1 or 2 points, kind of when I contacted Joseph. So that's why I kickstarted the project, just to make sure that we had something that was there if needed.
Yeah. And even if it doesn't get used for this pandemic, could be, it's a good thing to have ready for others, isn't it? So, Margarita, you said there's another question.
Yeah, there's another question about, I think Jakob should start answering it, because he studied at Imperial to do his master's. So one of our listeners asking, does biomedical engineering in Imperial entail aspects of other engineering, such as mechanical, electrical, and robotics?
I think it's probably one for Joseph and Michael.
Yeah, this is.
Oh, I'm sorry. I thought.
Yeah, biomedical engineering degree.
Sorry, repeat that question one more time.
Yeah. If biomedical engineering in Imperial entails aspects of other engineering, such as mechanical, electrical, and robotics.
So that's the beauty of bioengineering. There are so many different parts of it. As Joseph was saying, you really choose where the scale is, or where the line is between the interface between the different engineering disciplines, computing, electronic, mechanical, and bioengineering. And you really get to choose your projects. So when you do your projects, you choose which sort of field you want to have them in, and you sort of develop those skills inside your projects, get to know if that's actually what you want, or if you want something a little bit more different.
So it's really broad. You have a lot of options.
Yeah, it's really broad. There are quite a few options, and you get to, it's sort of university is sort of a place where you get to understand more about yourself and what you're actually interested in. And you do that by doing several projects, seeing whether something is actually what you want. You get to do 3 projects, so 1 every year, in your second year, third year, and your 4th year. And through those projects, hopefully you learn something about yourself and what you actually want to, what you want to actually do, and you move either towards that field or you move into a different field.
Yeah. And as you've shown, some of the students this year have been working actually on this project, which is, again, very exciting to get involved with projects that, can make a real difference immediately. Yeah.
Yeah, I'll just add, obviously, I'm new to the kind of an honorary bioengineer from this project. What's been really interesting for me as a kind of outside thing coming in is actually just wandering around the labs, and you'll see a lab like doing some of the work that Joseph was doing was on mouse eyes. There's an entire floor at Imperial doing robotic surgery. In Jen's lab, there's cameras measuring kind of lymphatic systems. There's just any sort of project you can think of seems to be in the Department of Bioengineering.
Yeah, I worked collaboratively with your head of bioengineering originally when we set up the Centre for Blast Injury Studies, and again that was really exciting because we had the bioengineers and the physicists and then the biologists, and it was a very challenging project, but yeah, again really interesting. And then we were dealing with lungs, because one of the problems with blast injuries is, as you were showing, how fragile lungs are, and they are one of the organs that gets sort of most damage with a sort of blast injury. Right. Any other questions, Margarita?
I have one. I was wondering how difficult it is for them to work with people from other areas, other disciplines, because I was watching your presentation and I felt like I don't know anything of that. I can't understand what they're saying. I have so many questions. And is it hard for you to work with someone that is a nurse or a doctor or a biologist? Can you fill the gap?
Engineers. So maybe Jennifer, how do you
cope with that?
Yeah. So I mean, I think one of the really beautiful things about bioengineering is that you have so much access to clinical settings and clinical staff, whether it's doctors, nurses, technicians, etc. So I know even in my PhD, I worked quite closely with medical doctors. Here on this project, we're working closely with medical doctors. So there's a lot of exposure in bioengineering to clinical to clinical staff. So from that perspective, I think that, you know, there's not as much of a disconnect as you maybe perhaps think. And I think the other thing too with bioengineering that you have to realize as well is that you do learn a lot about physiology, you do learn a lot about anatomy, maybe perhaps more from the perspective of engineering, but you can still speak that language. And so there's a common ground there, I think, between the engineers, bioengineers, and clinicians or other clinical staff that, you know, that makes it an easy collaboration, I think, from that regard.
So Jennifer, do you think that there are opportunities to work with medical problems in other animals, or it's just mainly in humans when you're studying bioengineering?
No, no, absolutely not. I mean, there are there are research groups within our department that do work purely on animals, or for example, in insects. We do have a couple of groups that look at insects. So, I mean, bioengineering is not always just restricted to humans. I mean, I think it makes up perhaps a majority of what we look at, but by no means are we limited to only that domain.
But I think one of the key things about this interdisciplinary working is that you have to be able to communicate your science in a way that other people can understand. So we just had a really beautiful demonstration of that with here showing us about pressure and Boyle's law, which I remember Boyle's law from GCSE, but even the sort of compliance and resistance, those sort of that terminology, and being able to explain it in that way such that the biologists understand is really important. So you do have to, in a way, explain things simplistically, even though you're dealing with experts, and there's a lot of trust. And I think that's why, for me personally, it's, you know, if you're somewhere like Imperial, everybody here, you know, everybody is fantastic scientists. So, you know, whoever you work with is going to be an expert and going to be top of their game. So it's always a pleasure to sort of, you know, work collaboratively. And I think the other thing that was really clear from what Jakob was saying, if you need the clinician, because there are certain things, say if you were developing this ventilator, you'd be thinking about ventilating the lungs and going in and out. You might not necessarily have thought of things like about the fact that they have to pull off excess liquid, and when they're pulling off that excess liquid from the lung, you have to ensure that the lungs are still ventilated. So how do you, you know, make the system work for, you know, on a practical level, because things are always more sort of complicated when you actually get into the clinic. And like all of Jennifer's work, looking at the sort of difference in the, you know, the stiffness of those lungs. And I think you were talking about fibrosis, and just to make sure people are clear about that, with COVID-19, this fibrosis, it's like scarring of a tissue. So if you imagine your skin, when you know, cut your skin, you get a scar initially, and that scar obviously doesn't have the same, is very stiff compared to the surrounding skin, and that same process is sort of going on in your lungs. You get all these scars formed, and that means that your lung isn't as elastic, so it's not sort of behaving in the same way. So I wondered the other thing, how does your JAMVENT cope with people because presumably it has to be adjusted depending on how big people are, how big their lungs are, and all the rest of it, and maybe underlying lung diseases that they have. Is that fairly straightforward as well, or
that's clinical settings? So generally you would set the tidal volume, so the amount, the size of each breath, based on a person's height rather than their weight, because if you're 300 kilos, your lungs aren't 3 times bigger than someone who's 100 kilos. So, and we do that again, that's one of those other reasons we do protect the mechanism. The way we do our exhalation actually is very good for is unique actually in ventilation. We kind of came across a kind of unique way of solving that problem. But actually a lot of it's to do with, that's more to do with how a clinician sets the settings rather than the kind of innate features of the ventilator.
And one last quick question. What you mentioned cost. The cost thing was really important for you. So what are the relative costs of one of your sort of fancy ventilators that you'd normally have in the clinical setting versus your JAMVENT?
Yeah, so a top of the line ventilator will be anywhere from £20,000 to £50,000 a unit. Generally about sort of 30-ish, I think is probably what we're paying for them in the UK. Our kind of parts cost at the moment is, and this is about £1,500 to £2,000. Right. But so obviously, we're looking at a factor of 10. Obviously, that would increase slightly with regulatory staff and inevitably kind of extra costs that creep in from manufacturing. But certainly on the order of kind of potentially up to 10 times cheaper.
Yeah,
and there's also the fact of buying the ventilator in the first place is one part of the cost of it, but for applications, one of our long-term uses of the ventilator would be in low and middle income countries where actually maintaining the devices are really going to be a large cost, and if it's not easy to maintain, it just won't get used anymore. But because we did the design with, as Michael mentioned, these very simple valves, they can just be easily replaced, and so the cost of maintenance of our system would be significantly lower and significantly easier than other designs.
Yeah, and I can imagine if you have people, say, working, I don't know, in the Red Cross or that, and you have engineers there that are working, they could be trained quite readily to do MOT of these devices. What about expertise required to use them in a patient, though? Would you still not need somebody with your sort of expertise, Jakob, to actually be able to use this on a patient?
Yeah, you do, but I think a lot of places the expertise is there. They just don't have the equipment.
Okay.
And obviously a pandemic scenario that we're kind of in at the moment, where hospitals are potentially getting overrun, you'll have that expertise. It's just spread a lot thinner.
Okay, great. That is really brilliant. It's been really interesting, and I realise that we've sort of gone over time, but that's a fantastic collaborative effort that has been going on during lockdown, and it's really quite incredible that you've got so far so quickly. And obviously it's a credit to all those people sort of working as a team and obviously having the great ideas and everything, so and a common goal. So it's fantastic to see this type of science. I think it's really inspiring for everybody to see what can be achieved. I mean, we've heard it in terms of whether it's sort of making hand sanitizer or actually, creating a new vaccine. It's just quite amazing how people are coming together. And this is just, we're just highlighting obviously what's going on at our university, and this is happening all across the world as well. There are different groups working collaboratively together to sort of really fight this pandemic. So, and I think that just shows, the importance of science, to addressing the big sort of global questions, and, whether that's climate change or the next pandemic, scientists are the people that are the problem solvers. That's what we like doing, is solving problems. So it really just leaves me to say thank you really to our speakers, to Jakob, Joseph, Jennifer and Michael, for their really excellent and really clear talks. Thank you to Margarita, as always, for moderating the session, and Sam for producing the session. So now I work in the National Heart and Lung Institute here at Imperial. And as well as scientists like myself who study heart and lung disease, and we're about developing new therapies, we have many clinical academics whose work life is normally divided between them working as doctors in hospitals and working as clinical scientists in laboratories. Now, during the lockdown, these clinical scientists went back to work full-time in the NHS. And tomorrow we're going to be chatting to some of them. Tomorrow at 2 o'clock, we're going to be talking to some of NHLI's respiratory and cardiovascular clinicians who have been working on the front line in Hammersmith and the Brompton hospitals treating those COVID-19 patients. So thank you all for joining us today. Please fill in the survey that I think Sam has just popped in the chat on the YouTube. Enjoy the rest of your day and hope to catch up with you tomorrow. Goodbye from all of us.